In objectives 1 and 2, you learned about exponential and logarithmic functions, and you learned a little bit about the graphs of each of those functions. In this objective, we're going to dive a little bit deeper into the graphs of exponential and logarithmic functions. We're going to be able to identify and describe characteristics of these graphs, and we're going to be able to sketch translations of these graphs as well. We'll start with overviewing exponential functions. So I've graphed here a couple of different exponential functions. We saw in objective 1 that exponential functions might be growth, where they're going to be kind of going up from left to right, or we might have exponential decay, where they're going down from left to right. And we saw kind of the deciding factor between that is that we have growth when the base is greater than 1. And we have decay when the base is less than 1. And so I've got here several different examples. We in the red here, we have 2 to the x, and then 3 to the x, and then 5 to the x, and then 10 to the x. And we see that as the base gets bigger, my graphs kind of get steeper. They increase more quickly because my growth rate is bigger. And then on the other side, going down, we have 1/2 to the x, and 1/3 to the x, and 1/5 to the x, and 1/10 to the x. And we see that as our base gets smaller now, we're going to decrease more steeply because our growth rate is even smaller. One thing that I really want to point out on all of these is that all of these graphs go to this same point. We saw this a little bit in the first objective, but let's just really hone in on this, that all of these graphs pass through the same point, 0, 1. And that's going to be because a to the 0 equals 1 for any positive base, as long as a isn't 0. So while all of these graphs with different bases look a little bit different, they have really similar properties, even if the graphs themselves might be a little bit steeper or go up or go down in different places. So we're going to talk about some of the characteristics that these graphs might have in common. So first we'll talk about the domain. And just to refresh your memory, the domain is all the x values that have graph associated with them. And I see here that no matter what exponential I'm thinking about, if I'm thinking about 2 to the x or 10 to the x or 1/3 to the x, I see at 2 to the x, every single x value has graph associated with it. And 1/2 to the x, every single x value has graph associated with it. So I would say actually that my domain is all real numbers. -infinity to infinity is how we would write that in interval notation, or all real numbers. The range, you might recall, are the y values we have, or the y values that we have graphed for, all the y values that we could get out of the function. So for thinking about the range, I'm going to be thinking along my y-axis, what kind of y values can I get out? And I see that, let's see, if we think about 2 to the x, I start getting a lot of small y values. And then this increases, and I think I should be able to get all my y values going up on this axis there. I should be able to get all those y values as that graph goes up and up and up. And over here, I'm going to get really, 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 really small. And so I want to pause and think real quick, is there a maximum y value that I can get out? And I don't think so. I think that my graph is going to increase towards infinity there. So I would say that my maximum y value, I would say actually would be like infinity. There isn't one. That was maybe a bad infinity. There we go. And is there a smallest y value we can get out? They're getting smaller and they're smaller and they're smaller. And it looks like they're never getting less than 0. Even if I'm thinking about the ones that are decreasing, I start with really big values. And I'm decreasing then, and my values are getting, actually they get closer and closer to 0, but they never actually touch 0, in fact. We get really, really, really tiny decimals out, but we never get 0. So our range is going to be 0 to infinity, and I'm going to put a parentheses on that to note that we never get 0 itself. So we might call this all positive numbers. We can also think about, in general, if we have any x-intercepts or y-intercepts. Remember that x-intercepts are where we touch this x-axis, and indeed I have no x-axis intercepts. The graph never touches the x-axis, so I would have none here. But for my base exponential, for anything in the form a to the x, as long as I'm not multiplying by anything else, my y-intercept is always going to be the point 0, 1, right? They all go through that point right there. Another characteristic we might think about is what we call an asymptote. You may have heard that word before, or you may not have. An asymptote is a line that kind of guides the behavior of a graph. You might have heard it before in the context of rational functions. Rational functions like 1 over x have a vertical asymptote. Exponential functions, or at least the base a to the x, has a horizontal asymptote, actually, at the line y equals 0. I'm going to sketch it in here for you. You do it as well. This line here, y equals 0, kind of guides the behavior. For my graphs that are growth, it kind of guides the behavior on the left-hand side, kind of in this end of my graph. For my decay, this asymptote guides the behavior on this end of the graph. But I would say that my asymptote has the equation y equals 0. It's the horizontal line, y equals 0. This is a good time to talk about whether or not my function is increasing or decreasing. And remember, when we say those words increasing and decreasing, we mean from left to right. Are my y values getting bigger, or are they getting smaller? And it seems like it actually depends on if we have growth or decay. When we have growth, my graph is getting bigger from left to right. And when we have decay, my graphs are getting smaller from left to right. So I would say that my graph is going to be increasing if a is greater than 1, and decreasing if we have a small a value, if it's between 0 and 1. And when we talk about asymptotes, it also leads us to think about what we call the end behavior. The end behavior would be a way to describe what happens at the infinities of this graph. When x is infinitely big or infinitely negative and big, what's happening to my y values? And it actually depends on if my graph is increasing or decreasing, or if I have growth or decay. Let's first think about if my graph is increasing. If my graph is increasing, I would say that when my y values are really, really negative over here, when my x values are really, really negative over here, my y values are approaching 0. They're getting closer and closer to 0 there. But as my x values get bigger and bigger and bigger to positive infinity, I would say, well, my y values are shooting up really fast as well. The way we would write this is like this. I would say when a is greater than 1, I would say that f of x rises to the right and approaches 0 to the left. Right? That's a way to describe what's going on here. My graph is rising to the right and approaching 0 on the left. We have kind of the opposite when a is between 0 and 1. Here we would say that f of x falls, oh no it doesn't, we would say that it rises to the left this time. And approaches 0 to the right. There's two other properties we want to talk about, and that would be whether or not there's 1-to-1, if the graph is 1-to-1, and if there's any symmetry. Remember, 1-to-1, if a graph is 1-to-1, it's going to pass the horizontal line test. And if I look at this, if I pick one of these, we don't want to think about all of them at the same time, but if I just think about one of these graphs at a time, I say Does it pass the horizontal line test? If I think about drawing a horizontal line, let's kind of sketch one of these individually, right? This is what growth kind of looks like, and this is what decay kind of looks like. And if I pass a horizontal line through here, I'm never touching more than 1 point at a time. It might look at it like it when my graph gets really, really flat here, but technically we're only touching one at a time. Even if that gets perceives to be a little bit flat, it technically isn't exactly flat. It's always a different y value there. So we would say that my graph is 1-to-1, no matter what A is, because it passes the horizontal line test. And sometimes we think about symmetry on a graph. Is there symmetry if I think about just one of these at a time? If I think about just my decay or just my growth, is there symmetry across the x-axis or the y-axis or some sort of line? And a lot of graphs have them, and this one turns out has none. There's no symmetry here at all. So these are just some key properties that we want to keep in mind when we talk about graphs of exponential functions. We can talk about these properties without talking about one specific base, one specific exponential function. I could just say, oh, exponential functions in general have a domain of all real numbers, and exponential functions in general are 1-to-1. If an exponential is a growth, then it's going to be increasing on all real numbers. We could say those generally without even knowing what our base is, which is pretty cool that we can say those all together.